So here are the group problems for lecture exam 3. The first one basically asks about heart rate and how we control heart rate in order to homeostatically control mean arterial pressure. So what we need to look at is we need to look at the various aspects that look at that. So the reason why we do that, remember the equation mean arterial pressure equals stroke volume times heart rate times TPR. So we'll be on the heart rate part, and then we'll look at the stroke volume and TPR in the next couple questions. So what we're looking at, and this is always true of any homeostatically controlled variable, we need to consider the intrinsic and extrinsic influences. The intrinsic are from within the system or organ itself. That is also known as auto or self-regulation. The extrinsic influences always involve a couple different things. We always have to look at the role of the ANS, the autonomic nervous system. We always have to look at the role of what hormones play. And in addition, there are sometimes other factors that we may need to consider in terms of that control. So heart rate is pretty straightforward. Heart rate has units of beats per minute. I think you all know that. So we'll look at the intrinsic control first. So how do we intrinsically control heart rate? The first way is again through autoregulation, although some people argue this really isn't a control mechanism because there's no evidence that the SA node, right, that would be the intrinsic, that's what causes the normal beating of the heart, that the SA node has any influence in terms of changing itself to try to control heart rate. All of the changes to the SA node come from extrinsic factors. Okay, so the adjustments come from extrinsic factors, but we still have to look at the basic SA node rate, right, that is genetically set. So in a sense, it's a factor, and I believe that it's probably the best way to do it is consider that the SA node is the intrinsic factor by setting the basic rate, and the adjustments come from extrinsic mechanisms. For the extrinsic control, right, we always, like I said, look at the ANS. When we look at the ANS, you ask, does both this parasympathetic and sympathetic systems, right, go to the place we're worried about? So we're worried about primarily for heart rate, the SA node and the AV node, and both the parasympathetic and sympathetic systems go there. So those two antagonistic systems influence the SA node and the AV node. They have independent branches and they're controlled separately, but they're antagonistic. So if the parasympathetic, for instance, would be going up, the sympathetic would be going down, right, with that antagonistic relationship. The parasympathetic branch, right, is inversely related to heart rate. So if the parasympathetic system is stimulated, the heart rate will go down. If the parasympathetic is withdrawn, if it decreases, the heart rate will go up. Studies have shown, though, and we talked about this back in lab 1314, that the parasympathetic has a huge influence at rest. So individuals without a vagus nerve, cranial nerve 10, right, their heart rate will jump without the vagus nerve influence from about 70 to 100 beats per minute at rest, which shows it's got a huge influence in terms of how it helps control heart rate. The sympathetic system, right, stimulates beta 1 receptors. The parasympathetic, remember from the ANS, would be the muscarinic receptors. And the heart rate increases because of the beta 1 receptor influence. The nerves that go to the heart from the sympathetic side are called cardio-acceleratory nerves, which actually makes sense because they speed up the heart. So cardio, heart, acceleratory, speed up. The sympathetic is directly influences the heart. So if sympathetic goes up, the heart rate goes up, and so on. It has much less influence at rest on the heart. It has more of an influence when the heart rate gets over really about 120. but it's about half and half between 100 and 120, and the sympathetic is the primary influencer after 120, which means the parasympathetic is the primary influencer below 100. And one of the kind of pieces of evidence for that is that if we cut the cardioacceleratory nerve, right, the one that speeds up the heart rate slows down a little bit. Usually it's like less than 5 beats per minute. So it shows us that the cardioacceleratory nerve, the sympathetic nerves, do not have a huge influence at rest. Okay, so the influence of the heart and what's happening is a two-part question. One, what is the heart rate range, and then what's happening there. So for instance, if we said, oh, heart rate went from 80 to 90, what was the primary cause? Since it's below 100, it would be the parasympathetic system. And since heart rate went up, it would be the parasympathetic withdrawal, the parasympathetic decreasing. Hormones also play a role. And all of our hormones have a positive chronotropic effect. Remember, chronotropic refers to heart rate. Positive means it goes up. So the hormones all have an increase effect on heart rate. Specific examples would be epinephrine and norepinephrine, so adrenaline and noradrenaline, if you look at it in a different way. Those also stimulate beta-1 receptors in the heart and do the same thing that the sympathetic system does. So sometimes they're known as sympathomimetics. All right, so sympatho means it's the sympathetic system. Mimetic means it mimics it. So epinephrine and norepinephrine are known as a class of hormones called the sympathomimetics. In addition, the thyroid hormones, T3 and T4, so that is triiodo and tetraiodothyronine, and those also increase body temperature, which then influences heart rate. Other things that cause an effect on heart rate is heat. The higher the body temperature, the greater the heart rate will be, and that's often due to the increased demand for oxygen. So those are the intrinsic and extrinsic controls of heart rate. Okay, so the second variable we'll look at is stroke volume. Again, remember our mean arterial pressure equals heart rate times stroke volume times TPR equation. Stroke volume has the units of mils per beat. Okay, so stroke volume has the units of mils per beat. We'll look at it intrinsically and extrinsically like we just did before. So the intrinsic control of stroke volume has to do with what we call the Frank-Starling law of the heart. The Frank-Starling law of the heart is an intrinsic autoregulatory mechanism. And what happens is, here's kind of the colloquial version, pump what you get. So what will happen is the greater amount of blood that comes back to the heart, the ventricle, the greater amount of blood the ventricle will pump out. So it's based on the volume of blood in the ventricle before it is ejected. So if you remember, that is known as the EDV for end diastolic volume. Okay, so the end diastolic volume. So if we increase the end diastolic volume, right, if we increase that, then we're going to increase stroke volume. So they're directly proportional. Okay, and what happens is when we put more volume in the heart, we get more stretch, and that leads to an increased number of cross bridges. And if I have more cross bridges engaged in my muscular contraction, I'll have a stronger contraction. And if I have a stronger contraction, then I'll get an increased ejection of blood, a stronger stroke volume. So again, increased stretch equals increased sarcomere length, which increases cross bridges, which increases contraction strength, which increases stroke volume. Okay, and this is where primarily the end systolic volume, we mentioned that during lecture, that it's highly regulated, and this is the major place where it is. Okay, so the more blood we put into the heart, the more we pump out, because remember, the end systolic volume, the volume of blood left in after a contraction is a regulated variable, and it does not change much, if at all, within a person. So if your end diastolic volume is 30 mLs, for instance, so let's say, let's try to make a 3 a little better. If it's 30 mLs, right, if that's normal, and let's say your end diastolic volume is 100, right, that means your stroke volume would be 70. But if you put 150 mils in your left ventricle or right ventricle before ejection, right, then you're going to pump out 120. Why? Because your end systolic volume is still going to be 30 mLs. Since you started with 150, you're going to pump out 120. If for some reason you only put 60 mLs into your ventricle, right, then you're only going to pump out 30. Your stroke volume is going to be 30 because we're always going to have 30 left. And it's because of the Frank-Starling law that really makes this end systolic volume highly regulated. A similar concept, but different, distinctly different, is preload. Now, again, preload, the pre refers to before, and load is pressure. So preload looks at the pressure of the ventricle before ejection. So what's the total pressure of the ventricle before we eject blood? If the pressure is greater, then the ejection will be greater, so stroke volume will go up. Remember, blood or all fluids move because of a pressure difference. A greater pressure difference gives us a greater ejection of blood. So normally, and this is how pulse pressure is indicative of stroke volume. So normally, let's say, your blood pressure was 120 over 80, okay? And so the pressure that you have to overcome, right, is 80. And let's say then if your systolic pressure is 120, that means that's going to be the peak pressure of the ventricle for ejection. So the difference is 40 here, right? And since I have a difference of 40 for my difference in pressures, right, then I'm going to get X amount of blood, okay? Well, if for some reason my preload went up, let's say it went to 90, like during hypertension, so if I had a higher diastolic blood pressure I had to overcome, and my systolic pressure of my ventricle was still 120, that means my pressure difference is only 30. If I have a 30 pressure difference, I'm only going to be able to eject a smaller amount of blood because I have a smaller pressure difference. And the amount of blood that moves is directly proportional to this pressure difference. So the pressure difference, right, we know as the pulse pressure. So preload has to do with the pressure of the heart. It's also directly proportional, though. If preload goes up, ejection goes up, stroke volume goes up. And if preload goes down, then it goes down. So both the intrinsic mechanisms, Frank-Starling, which has to do with volume of the heart, and preload, which has to do with the pressure of the heart, are directly proportional to each other. Sorry, we're directly proportional. I guess the best way to say it is stroke volume is directly proportional to those things. Extrinsically, we also have to worry about a number of factors. And actually, I think stroke volume is the most complicated of the control factors. First would be the ANS, and the ANS is primarily sympathetic because what we're worried about now is the influence to the ventricles, right? Because that's what provides the stroke volume. And there's few parasympathetic fibers that go to the ventricles. It's believed that's true because if we overstimulated the parasympathetic system, we could cause the ventricles to weaken so much we couldn't pump sufficient blood to sustain life. So we see that with hormones as well, that we don't have any hormones that decrease the heart rate. We don't have any hormones that decrease stroke volume. And the reason why is if we had an abundance of that hormone, an oversecretion, then it could stop activity of the heart so much that we would die. If you have a hormone that increases activity, then yes, you'll have high blood pressure, you'll have hypertension, but the influence of that hypertension is not going to cause health problems until way down the line. So it's not an immediate death type thing like a decrease in heart rate would be potential if it was overstimulated. So what happens with the sympathetic system is it increases the inotropic state of the heart. Remember, inotropy was the contraction strength by allowing greater calcium conductance. Okay, so the calcium conductance increases during sympathetic stimulation. And the reason why is it opens calcium channels through the beta 1 receptors. So when we have the beta 1 receptors, it opens calcium channels. And the more calcium that comes into the cell, because the heart relies both on intracellular and extracellular calcium. So the greater amount of what they call calcium conductance, the greater amount of calcium that moves across the cell membrane in the cardiac muscle, that increases the cross bridging. As we said before, increased cross bridging equals increased contraction strength, which increases stroke volume. Okay, so it's the calcium conductance there. Since we open more calcium channels, we have more calcium come in, and that causes a greater role. This parasympathetic has the opposite effect, but it's not very great. It's doesn't have a huge influence because it's a sparse innervation. And that way, if we had a significant parasympathetic stimulation, your heart won't stop. In fact, that's the reason why we have the ventricular nodes, is to keep the heart rate beating even if you stop the SA node and the AV node. From the hormone perspective, extrinsically, I sort of mentioned this a minute ago, all of the hormones that we know of in the human body stimulate the heart to increase. Okay, so again, our epinephrine and norepinephrine, right, stimulate beta 1 receptors. So those are our sympathomimetics, right? They mimic the sympathetic nervous system, and therefore they do the exact same thing that the sympathetic stimulation does. So they open calcium channels through beta 1 receptors. That causes an increase in calcium conductance. That increases the cross bridging, and that increases contraction strength, which then increases stroke volume. So that's our hormone. There are no other hormones we have to worry about, and there are, like I mentioned, no hormones that decrease heart strength and contraction, stroke volume. For our other, we have an afterload. Remember, load meant pressure. So afterload is the amount of pressure pushing back on the ventricle. Okay, so pushing back on the ventricle. The afterload I actually explained up here, where the higher pressure that we have to overcome, because afterload is best estimated by the diastolic blood pressure of the aorta or the pulmonary trunk on the right side of the heart. The pressure you have to overcome, again, it leads to that pressure difference. And so if we talked about the diastolic pressure being 80 in one case and the systolic pressure 120, if we increased afterload, the diastolic pressure would go to 90, and that would give us less of a pressure difference. I didn't really do a good job explaining preload. If we increase preload, right, we would increase the pressure of the ventricle. So let's say it's 130, and that again would give us a bigger difference. So it's the difference in the pressures, the pressure difference, that really determines blood flow. So if I have to overcome a greater pressure, then my stroke volume goes down. Right? So one thing to kind of remember when we look at the parasympathetic system and the afterload, they're the only two factors that we discuss that have an inverse relationship to stroke volume. So if parasympathetic stimulation goes up or afterload goes up, stroke volume goes down. All right. All the other ones we've talked about, and we're going to talk about, have a direct relationship. If it goes up, then stroke volume goes up. An example of that would be venous return. Venous return is to pump blood out of the heart. In order to pump blood out of the heart, right, we need to get blood back to the heart. And so venous return, if we have an increase in venous return, right? We can increase the cardiac output because we have more blood coming back to the heart, which means we have more blood to pump out. Venous return is increased through a variety of mechanisms. One is venoconstriction. Remember, venoconstriction makes your veins more rigid, right? And allows blood to go directly back to the heart and not pool in the venous system. Remember, the venous system holds 60 to 70% of your blood sometimes. In addition, the muscle pump and respiratory pump. So remember, this was the action of your thoracic cavity or your muscles, especially in your legs and arms, that move blood back against gravity, that help push blood back from the lower extremities, especially back up to the heart itself. So by moving your legs and walking around or running or breathing, even that pressure change allows the blood to be pumped back to your heart and increase venous return. So as an example, that's why when you finish exercising, you're supposed to walk around and move so that blood doesn't pool in your leg and you have adequate blood flow to your brain so you don't pass out. The last factor would be calcium conductance. We've kind of mentioned calcium conductance before because that's how the sympathetic system works. It increases the entry of calcium into the cardiac cell. However, it's an independent mechanism because there are other ways to increase the entry of calcium into the cell, and that'll give us a greater stroke volume due to the increase in cross bridges. Examples of increased calcium conductance, caffeine will do that. So caffeine, one of its mechanisms of action is it opens calcium channels, and you get a stronger beat of the heart there. You can also do it with even body position. So sometimes if you lay on your side, you can feel like your heart skips a beat. It's because you're having a PVC, and that's due to the excitability of the heart and the increase in calcium conductance. It's not dangerous if you have a healthy heart, but the more calcium we get into the heart, the better off we will be in terms of contraction strength. So that is the stroke volume one. And then we'll get to the last one, which will be TPR, the total peripheral resistance. Okay, so we continue on with our explanation of the control homeostatically of mean arterial pressure. We already discussed heart rate and stroke volume. And since our equation, mean arterial pressure equals heart rate times stroke volume times TPR, we will now look at the resistance. Resistance in humans is determined in our blood vessels by Poiseuille's law. Remember that Poiseuille's law has to do with the tube length, the viscosity of the fluid, and the tube radius. So here it is right here. Poiseuille quantified that in a tube. So 8L times N over R to the fourth, small r. So big R resistance equals a coefficient we're not going to worry about, times L, capital L is length, the length of the vessel, times N, N is the viscosity, divided by small r, that's the radius, to the fourth power. Okay? So as we've discussed before in lecture, that the length of a blood vessel doesn't really change, and appreciably not in an immediate time frame. The viscosity doesn't change to change blood pressure. Yes, if length or viscosity changes, we can't forget about it because it will affect blood pressure, but we don't change those variables to change blood pressure and control it. But we do change the radius. The radius is the half the diameter, right, of the blood vessel. And it has a huge effect because it's raised to the fourth power. So small changes in radius have a huge influence on the actual blood flow itself. And that's how we primarily control minute-to-minute changes in TPR, is changes in radius. So basically, it comes down to this kind of simplified equation, small r for control equals big R equals 1 over R to the fourth. Okay? If we put Poiseuille's law into the blood flow and pressure equation, right? So remember, Q flow equals pressure over resistance, right? So if we look at the flow equation here, we have pressure, so there's our pressure. Since we just flip Poiseuille's law upside down to put it on the bottom, right? So here R equals, it's actually 1 over R on this side, on this equation, it's 1 over R. So we just flip it upside down and we get P times R to the 4th divided by 8L times N. So that's Poiseuille's law. And that's what we really use to quantify, not to quantify so much, but to control the radius of a blood vessel, which ultimately controls resistance, which ultimately controls total peripheral resistance, right? And that then determines our mean arterial pressure. So for TPR, right, total peripheral resistance, it has units of minutes times millimeters of mercury times ml. So they're kind of weird units. They're often called PRU, or peripheral resistance units. That's what it stands for. PRU, peripheral resistance units. And they're kind of strange, but they allow the mean arterial pressure equation to work. So when we look at the intrinsic control of TPR, there are two mechanisms we have to worry about. The first is called the myogenic mechanism. Myo refers to muscle, right? Genic means come from. So the myogenic mechanism comes from muscle itself, and it's when an arteriole can control its own diameter, right? And it responds to stretch and pressure exerted on the walls of the vessel. So as blood moves through a arteriole, remember the arteriole are the greatest sites of resistance in the human body, right? So those are the ones that have the greatest control in terms of flow. As it moves through an arteriole, if we have an increased stretch or pressure exerted on it, the wall of the vessel will sense that and change its size to accommodate it. So it's called the myogenic. So myo means muscle, genic means that's where it comes from. So it's an intrinsic mechanism because it's related to the actual arteriole, the blood vessel itself. The second one is called the chemical mechanism. The chemical mechanism refers to the idea that the arterial diameter is changed by chemicals, okay? Since this is an intrinsic control, these are local chemicals, right? So they're local chemicals. They're the ones produced in the blood vessel itself. Sometimes the local chemicals are called metabolites, all right? Because all of these, adenosine, right? Carbon dioxide, histamine, lactic acid, potassium, nitric oxide are all examples of those local chemicals. So they work by diffusion. They're often released in greater quantities during muscular movement, an increase in metabolism. That's why they're called metabolites. And they're all vasodilators. So all of our local chemicals cause vasodilation. So they allow the resistance to go down. Remember, as the blood vessel gets wider, there's less resistance, right? And it works because of this factor. So if we have an increase in metabolism locally because of an increase in muscular movement, it would be logical that we would want to increase blood flow. So to increase blood flow, if we dilate the blood vessel, that would allow more flow to go to that area and help partition the blood flow to the areas of need. So the chemical mechanism, very important mechanism in terms of that. To be honest, we're not really sure which of these works, what they call in vivo, in the body naturally, but in clinical trials and tests, we have noticed that any one of these, if injected into a blood vessel, will cause dilation. So perhaps all of them work in concert with each other to help that happen. Extrinsically, right? So those are our two intrinsic ones, myogenic and chemical mechanisms. Extrinsically, we have the ANS, right? And in this case, it's sympathetic only. Remember, if you remember back to the sympathetic system, blood vessels which we're talking about, right? Because that's going to where TPR is going to be exerted. Blood vessels are only controlled by the sympathetic system, so there's no parasympathetic system, right? So there's no parasympathetic fibers that go to blood vessels, so we don't have to worry about it. Matter of fact, if you think about it, when we look at the stroke volume and the heart rate stuff, so let's start at the heart rate. The heart rate, we had an equal influence of sympathetic and parasympathetic. For the stroke volume, we had mostly sympathetic and a little parasympathetic. And now for this one, we have all sympathetic, no parasympathetic. So as we kind of move down that list from heart rate to stroke volume to TPR, the parasympathetic influence decreases and then eventually becomes none. So what sympathetic does is it keeps what we call the vasomotor tone. The vasomotor tone is the constant signals from the brain to the blood vessels that cause vasoconstriction. If the frequency is increased, then we get constriction of a blood vessel, so TPR goes up. And if the frequency is lowered, then we get dilation and TPR goes down. So the sympathetic system controls the diameter of the blood vessel that way. We also have hormones. And as always, we have our friends epinephrine and norepinephrine. Remember, those are sympathomimetics, so they mimic the sympathetic nervous system. And all of those, because the sympathetic causes constriction, if we increase it, then those cause constriction. They all increase TPR. In addition, hormones like oxytocin or antidiuretic hormone, which is also known as vasopressin, and angiotensin 2 also cause an increase in the constriction of blood vessels. So those are also constrictors. Note, like we've kind of seen before, there are no vasodilators that are released as hormones. All the vasodilators are local and all the vasoconstrictors are global as hormones. And again, it's sort of the same line of thinking we had before. If we have a hormone that causes vasodilation and we overproduced it, that hormone could cause vasodilation to such a degree that our blood vessels dilate so much that we can't return blood flow to the heart. And if we can't return blood flow to the heart, we can't pump blood out, and we would die. So that's the hormones. The good news for you is that there's no noteworthy other factors we're going to talk about. There are some, we're not going to worry about them here in class. So that's the first half of the group problems, looking at the three major controllers of mean arterial pressure, heart rate, stroke volume, and TPR.